This particular video is going to be about a set of curves known as conic sections. Here's a cone, and conic sections are formed by taking cuts into this cone in various ways. Now, the curves that are formed by taking these particular cuts or sections are very old. They were known to the ancient Greeks from about 350 BC onwards. But not only are they very old, but they also are very modern. The dish aerial that's outside your house that brings in sky television is based upon the reflective property of one of these conic sections that we're going to be having a look at. Jodrell Bank Telescope, a radar telescope that pierces deep into the universe, picking up signals, recording them for us, again is based upon a reflective property of one of these conic sections. So old though they are, ancient even though they are, they have very, very important modern uses. So let's have a look at our cone. Let's begin by describing some features about the cone itself, which I'll need in order to describe the sections and the curves that we're going to see. First of all, let's think about the axis of the cone. Now, that's the line that runs from the point down through the centre of the base and out there. So that's the axis. The generator of the cone, well, that's any line that runs down the side of the cone like that. And the generator, think of it as being a pendulum, a piece of string tight to there. It swings round here and it maps out this curved surface of the cone. So let's begin by looking at the cuts or sections that we can make. Well, one of the simplest sections that we can make is to cut across and perpendicular to the axis of the cone. And what do we get? We get that well-known curve, the circle. Okay, let's not now cut perpendicular, let's cut at an angle. So we're going to cut at an angle to the axis of the cone. We're going to keep the cut within the physical dimensions of the cone, and what do we get? We get a curved surface, a closed curve again. This time it's an ellipse, a kind of flattened circle if you like, but its name is an ellipse. Let's put that back on, and now let's take a cut which is parallel to the generator, parallel to the edge of the curved surface. So there's our edge of the curved surface, and this is the cut that we're going to take parallel to that edge. So we make the cut, and there we've got an open curve this time, not a closed one, it's an open curve, and it's called the parabola. Putting that back together, what I want you to imagine now is a double cone. Now, what do I mean by a double cone? I mean another cone sitting on top of this one, point to point. So imagine we've got this cone here, and we've got another cone up here. And again, I'm going to take a cut, which this time is going to be parallel to the axis of the cone, coming straight down there. And you can see the cut there. Now, once I make it, there I've made the cut, I'll actually be making the cut through the cone up here. And so there'll actually be two pieces to the curve. One from the upper cone and one from the lower cone. And that's a hyperbola. It's got two branches to it. So those are our three conic sections. Sorry, miscounted. Those are our four conic sections. The circle, the ellipse, the parabola, and the hyperbola with its two branches. Now, the conic sections were first discovered by Monachus in about 350 BC. Monachus was an ancient Greek. He, in fact, had three different cones, but he took the same cut in each cone in order to generate three of them. Here we're disregarding the circle because that's obviously the simplest cut to make. Later, Apollonius, who was around about 200 BC, generated this idea of making the cuts all in exactly the same cone. So, we've seen what these curves look like, and we've seen how they are generated. And now what we want to do is to explore their mathematical equations. If we don't explore these mathematical equations, then we won't be able to deal with these curves and find out what their properties are. So, let's have a look at a definition of these curves that will actually help us to calculate them. What I want, first of all, is a straight line. And this straight line has a name. It's called the directrix. And I want a fixed point. I'm going to label that fixed point F, and it's F for focus. Take any point in the plane, let's call that the point P. And then we've got P must be a distance away from this fixed straight line. Let's call that point M. And that's, of course, a right angle. And it's also a distance away from F, the focus. And so the definition that we're going to use is that PF, the distance of the point from the focus, is equal to a constant multiple of the distance of the point from the straight line. And that constant multiple we use the letter E to denote. And so PF is equal to E times by PM. Now, what happens? Well, this point P follows what we call a locus. Let's just write down that word, locus. What do we mean by a locus? Well, it's simply a path. The point P follows a path governed by this rule. This letter E. E is used to stand for what we call the eccentricity of the curve. And we get our different conic sections for different values of E. So, if E is between 0 and 1, the curve that we get is the closed curve, the ellipse. If E is equal to 1, the curve that we get is the parabola, the open curve, but with a single branch. And if E is greater than 1, the curve that we get is the hyperbola. Remember, that was the open curve with the 2 branches. Now, in what happens in the rest of the video, we're going to deal with this particular curve in some detail. We'll look at some of its properties and we'll just relate, say, what the equivalent properties are in these 2 curves. But this is the one that we're going to deal with in detail. And the sorts of mathematics that we use and the ways in which we work, if replicated, will enable the same sorts of properties to be proved and established in the ellipse and the hyperbola. So, let's go on and have a look at the parabola. So, let's draw a picture. So I'm going to set up some coordinate axes, x and y. I'm going to take my straight line, my directrix, there, and I'm going to take my focus there. Now I need some measure, some scale, some size. So I'm going to say, I'm going to take the focus at the point A0. Now remember that for our parabola, PF is equal to PM because E, the eccentricity, was equal to 1. So the distance of our point P has to be the same from this line as it is from this point. And of course there's an obvious point, namely the origin, that perhaps we'd like to be on this curve. So that means that the directrix here is going to be at x equals minus a. So let's put our point P, let's say there. There is PM, that's our point M, and there is PF. We'll call this the point X, Y. So, what's the locus? What path? What's the equation of that path that P is going to follow as it moves according to this definition? Well, one of the things we'd better do is we'd better write down what are these lengths. PM equals, well, from M to the y-axis is a distance A, and there's a further distance of x to go before we get to P. So PM is A plus x. What about PF? As we look at PF, it's the hypotenuse of a right-angled triangle, which we can form by dropping a perpendicular down there. So we can see that PF will be, when we square it, PF squared will be equal to that squared, which is just the height, y, plus that squared. Well, up to there is x, and up to there is a, so that little bit in there is a minus x squared. So this is PF squared. Let's just check that again. PF is the hypotenuse of a right-angled triangle, so using Pythagoras, PF squared is that squared plus that squared. That's the height y, that P is above the x-axis. Up to there is x, up to there is a, so the distance between there and there is a minus x. So now I need to equate these two expressions, and first of all that means I've got to square PM, because if PF is equal to PM, PF squared must be equal to PM squared, and so we can substitute this in. So instead of PF we have y squared a minus x all squared, and instead of PM squared we have a plus x all squared. Now we need to multiply out this bracket, y squared plus. Now let's just do the multiplication over here. A minus x all squared is a minus x times by a minus x. So with a times by a, that gives us a squared. With a times by minus x and minus x times by a, which gives us minus 2ax. And then with minus x times by minus x, which gives us plus x squared. Equals. Let's have a look at this bracket. It's a plus x all squared. So it's going to be exactly the same as this one, except with plus signs in. So we're going to get a squared plus 2ax plus x squared. Now let's have a look at this. We've a plus a squared here and a plus a squared there. So we can take an a squared away from each side. We've a plus x squared here and a plus x squared here. So we can take an x squared away from each side. We've minus 2ax here and plus 2ax there. So it makes sense to get those ax's together by adding 2ax to this side and adding it to that side. So if we do all that, we've got y squared. The two a squareds will disappear, subtracting a squared from each side. The two x squareds will disappear, subtracting x squared from each side. And adding the 2ax to each side, we get 4ax. And that is the standard Cartesian equation for a parabola. Now, this is a standard equation, and it is the equation with which we want to work. But sometimes, when we're doing these curves, it's helpful to have the equation described in terms of a third variable. A variable that's often called a parameter. And the parameter we're going to have in this case is the parameter t. So we've got an equation y squared equals 4ax. Now what we're looking for is a way of expressing x in terms of t and a way of expressing y in terms of t. Well, as we look at this, this says y squared equals 4ax. Now y squared is a complete square, it's a whole square, an exact square. I can take its square root and I'll just get plus or minus y. So can I do it over here? Can I choose an expression for x that will give me a complete square on this side of the equation? Well, 4 is already a complete square. If I want to make a complete square, I'd have to have a squared. So I need something in x that's got an a attached to it, so a times by a would give me a squared. And then I want to be able to take this exact square root. Well, the only thing, if I'm going to introduce this variable t that suggests itself and is sensible, is t squared. So if we put x equals a t squared, then y squared is equal to 4a times a t squared, which is 4a squared t squared. And so y is equal to 2at. And so what I've got here is what's called the parametric equation for the parabola. Now, that's our parametric equation, and this is our Cartesian equation. The one thing we haven't done yet is sketched the curve itself. So I just want to do that. So there's our x and y axes. There's our directrix through minus a. Here's our focus at a0. We know the curve is going to go through there, and its equation is y squared equals 4ax. Well, if we take positive values of x, we can see we're going to get that. But a positive value of x gives us a value of y, which when we take the square root is plus or minus. So we can see we're going to have that and symmetry in the x-axis. Notice we can't have any negative values of x because 4a is a positive number, times our negative value of x would give us a negative value for y squared. What about the parametric equation? X equals at squared, y equals 2at. What does this do in terms of this picture? Well, if we look at it, we can see x equals at squared. A is a positive number, t squared is positive. So again, we've only got values of x which are greater than or equal to 0. However, values of y can range from minus infinity to plus infinity. And if you like, t down here is minus infinity. Going round to t equals 0 here at the origin, coming round, if you like, to t is plus infinity there. So t is a parameter, and in a sense, it counts us around the curve. As t increases from minus infinity to plus infinity, we move around the curve. Okay, what about this curve? Well, one of the things that we want to be able to establish is what's the equation of the tangent to the curve at a particular point. So again, let's draw our picture of the curve, putting in the directrix, the straight line, putting in the focus, and putting in the curve. Let's take any point P on the curve. And the question we're asking is, what is the equation of the tangent to the curve? What's the equation of that line? Well, I've got P is any point on the curve. So instead of calling it xy, I'm going to use the parametric equation. X is at squared, y is 2at. So x is at squared, y is 2at. The question we're asking, what is the equation of the tangent? Well, it's a straight line. To find the equation of a straight line, we need a point on that line. Well, we've got it, at squared 2at. And we need the gradient of the line. And the gradient of the line, of course, must be the gradient of the curve at that point P. So we need dy by dx. But both x and y are defined in terms of t. They're defined in terms of another variable. They're functions of another variable. So if I use function of a function, dy by dt times dt by dx, then I can calculate the gradient. dy by dt, and let's remember that dt by dx is the same as 1 over dx by dt. In other words, dy by dx divided by dx by dt. dy by dt is the derivative of this. dx by dt is going to be the derivative of that. dy by dt is just 2a divided by the derivative of x, and the derivative of that is 2at, which gives us a gradient of 1 over t. So now we've got the gradient of the curve at that point, so we've got the gradient of the straight line, and we've got the point. So y minus y1 over x minus x1 is equal to the gradient. So that's a standard formula for finding the equation of a straight line, given a point on the line, x1, y1, and its gradient. So let's substitute in the things that we know. This is going to be our x1, this is going to be our y1, because that's the point on the curve, and this is going to be our value of m, our gradient. So let's just write down that information again. So our x1, we said, was going to be the point on the curve, x equals at squared. Our y1 was going to be 2at, and our gradient, m, which was dy by dx, was going to be 1 over t. The standard equation of a straight line, given a point on the line, x1, y1, and its gradient, m. And now let's substitute that information in. So we have y minus 2at all over x minus at squared is equal to 1 over t. Now, we need to multiply everything by t in order to get t out of the denominator here, and multiply everything by x minus at squared in order to get the x minus at squared out of the denominator. So we multiply everything by t, so we have t times y minus 2at is equal to, and we multiply everything by x minus at squared, and on this side it means we're multiplying by 1, so that's just x minus at squared. Multiply out this bracket, ty minus 2at squared is equal to x minus at squared. Now, here we've got at squared, a term in at squared, it's minus 2at squared, and here we've got another term in at squared, which is just minus at squared. So if I add 2at squared to each side, I'll just have at squared on this side, and this will just leave me with ty. So that's ty equals x plus at squared. And that's the equation of the tangent at the point P. Now, there is a reason for working out this tangent. It's not just an exercise in using some calculus and using some coordinate geometry. I've done it for a purpose. I want to explore the reflective property of a parabola. So first of all, let's think what that actually is, reflection. If we have a flat plane surface, then if a beam of light comes into that surface at an angle theta, the law of reflection tells us that it's reflected out again at exactly the same angle to the surface. So it comes in, it's reflected out again. What if we had not a plain flat surface, but let's say a curved surface? Well, what the law says is, I'm sorry, but a curved surface is exactly the same as a plain flat surface, except we take the tangent at the point where it's coming in. So the ray of light is reflected out at the same angle to the tangent that it made to the tangent when it came in. So that's the reflective law. How does this affect a parabola? Say we had a parabolic mirror, a mirror that was in the shape of our parabola. There's our parabola. What happens to a ray of light that, say, comes in parallel to the x-axis and it strikes the mirror? Well, when it comes in, it must be reflected. The question is, where is it reflected? What direction does that go in? The law of reflection tells us that if that's the angle theta that's made there, then that must be the angle theta that's made there. So what we need to discover is, if this is the case, where does that go? Where is that ray of light directed? And as you can see, this is all to do with a tangent to the curve, so it's quite important that we know what the equation of that particular tangent is. Okay, now we know what it is we're trying to do, let's set up a diagram, and on this diagram let's put some coordinates of important things. So there's the directrix and there's our focus, two very important points. Here's our parabola. Whoops-a-daisy. A bit better curve. Here's our point P. There. And here's our tangent to the point P. I'll call that the point T there. And a ray of light is going to come in like so. What I'm going to do is I'm going to join that to the focus. So here I've got this line here which is parallel to the x-axis. I'm going to call this n. So I've got a line here, Pn. And if I extend Pn back in a straight line, it's going to meet the directrix there at the point M. And there will be a right angle. Let's remember what the point P is. It's the point at squared to at. Okay. One of the things that we need to find is this point T down here. Let's remember the equation of our tangent. It's Ty is equal to x plus a t squared. And that's the equation of the tangent, pt. So at t, y is equal to 0. And that implies that x is equal to minus a t squared. That enables us to find this length here, tf. It must be that distance up to the origin, O, which is a distance at squared, plus that. So that's a plus at squared. We know that pf is equal to pm, because that comes from the definition of the parabola. But we also know what pm actually is. Pm is this distance a plus this distance here, which is at squared. So if we look at the argument that we've got here, that Tf is a plus at squared, Pm is a plus at squared, and Pm is equal to Pf, and this means that Tf and Pf have to be the same length. In other words, this triangle here is an isosceles triangle. Triangle FTP is isosceles. Okay, it's isosceles. What does that tell us? Well, if it's isosceles, it tells us that its two base angles are equal. So that's one equal side and that's one equal side. So that angle has to be equal to that angle there. Therefore, the angle FTP is equal to the angle TPF. Let me just mark those. That angle there is alpha, and that angle there is alpha. But wait a minute. This line and this line are parallel. So therefore this angle, NPF, is equal to this angle, PFT. Those two angles are both equal to beta, because this line is parallel to that line. They make a Z angle. Now, the angles of this triangle add up to 180, and here is a straight line, the angles of which must add up to 180. And so this angle here is also alpha. Hang on a minute. What we're saying is that the angle that this line makes with the tangent is equal to the angle that this line makes with the tangent. In other words, if this was a ray of light coming in here, it would be reflected according to the law of reflection, and it would pass through the focus. So any ray of light that comes in parallel to the x-axis, each ray of light is reflected to the focus. Now you can see how your dish aerial works. Your dish aerial is formed by spinning a parabola, so it makes a surface, a dish. The signal comes in and strikes the dish and is reflected to the receptor, that little lump that stands up in front of the disc, and the whole of the signal is gathered there. How else can we make use of this? Well, we can make use of it in searchlights, because we can turn it round the other way. If we put a bulb there at the focus and it emits light, then the light that emits will travel to the parabolic mirror and will be reflected outwards in a beam, a concentrated beam. Not one that spreads, but one that is concentrated and is parallel to the x-axis, to the axis of the mirror. So we see that a property of a curve discovered and known about by the ancient Greeks has some very, very modern applications. And indeed our society would not be the same without the kinds of properties that we're talking about now that exist in these conic sections.